Okay, hi.
Hello, sir.
All right. Let me open the slides.
شو بعمل لك؟ يعني بعمل لك ما تعملي ستريس على الموضوع.
Okay, let's wait a few minutes and then we'll start. So assignment 6 or 7? Assignment 7?
7.
7. Okay, so assignment 7 is out. It's on logistic regression and gradient descent. So it's due in 1 week. We'll try to have a session online on Zoom about it as well by Shady. The other thing I want to talk about is the midterm. So how is a week from now for the midterm? What is that? Hi, Rodrigo. So how about a week from now? So let's say next Thursday for the midterm. It's going to be on Moodle and it's multiple choice. So it's not really that difficult. Would that work?
We will have to cover all the material that we've taken.
Not up to support vector machines. So basically, we stop right before logistic regression.
So can we not take a new assignment then? Like assignment 7, we can take it after the exam?
We could do that, or we could postpone the exam, but let me see. Yeah, so I'll think about it and inform you by email. So most likely the assignment will go as planned. We could postpone the exam if you feel like you need some more time. But it's really, I mean, mostly like multiple choice questions. So it shouldn't be that difficult, yeah? So you can handle both the exam and the assignment. If there are previous, no, there's no previous. It's brand new.
The weight of the exam is still the same?
Yes, the weight of the exam is still the same. So it's what, was 20% or something?
Yeah.
Okay, yeah, it's going to be the same. Okay, I'll confirm with you later tonight. I'll think about it carefully and then confirm with you later tonight. And you have to accept my decision. Yeah, it's a dictatorship. That's cool. That's okay.
Okay.
Yeah. Okay. Good. Bye. So today we're going to talk about neural networks. Are you excited? I guess yes. Okay, I'll assume that's a yes.
You're lagging.
I'm lagging?
Yes.
Okay, so let's see what we do about this. So, okay, so this is the outline of the lecture. We're going to talk about stochastic gradient descent, then neural networks, and then backpropagation, which is the algorithm for training neural networks. Okay, so Rafa, so we're talking about the midterm being next Thursday, online on Moodle at the time of the lecture, a multiple choice question, a multiple choice exam. Okay.
Like, will we be on Zoom or we do it at home?
So I'll have to think about it. You'll do it at home for sure, but I'll have to see if we need to proctor or I will trust you and let you be on your own. Yeah.
Trust us, sir. Nothing can go wrong.
Yeah, right. Yes, until SVM, yes. Not sure, even if you're on your own, that would help, yeah? So it's not really clear whether that would make a huge difference, okay? All right.
Wait, do you mean the exam is hard?
No, I don't. I'm saying it just wouldn't make a difference whether you're on your own or with, you know, or if you're with some other people. Yeah, it's not hard. Yes, sir. Thursday class time. Okay. Yes, next Thursday. Good. So let's see what's stochastic gradient descent. We talked about gradient descent for logistic regression the last time. So logistic regression is this model, right, that uses like a probabilistic interpretation. And we used the gradient descent as an algorithm to minimize the loss function for logistic regression, which happens to be the cross entropy error. So the idea was to initialize the weights at random and then compute the gradient, right? So we were using logistic function, so using the sigmoid function, and the gradient of the sigmoid function was this formula, yeah? So -1/n, summation from n equal 1 to n, yn xn over 1 plus e yn w transpose xn, where w is the current weights, yeah? And yn is the label, and xn is the feature vector. That will give me a vector of gradients. And that's the direction I should take, or negative the direction I should take to update the weights. So I update the weights by setting them to the old weights minus eta times the gradient. Yeah, the gradient gives me the direction. So I should increase the W or decrease the W. It's either positive or negative. And the eta is the learning rate. So this step, how much should I update the weight? What's that, Ibrahim? Okay. And then I repeat this. So I keep repeating this a fixed number of iterations, so-called epochs, until either the error doesn't change or I reach this limit on the number of iterations. And then I return the final weights, W, as the model that I've learned. Okay. So this is how we did logistic regression. Good. Now, the problem is each iteration involves the whole training set. So if you look at this formula, right, to compute the gradient, I have to do really a summation over all the training set. Yeah. So basically, I take every instance in the training set and I compute this formula and then sum and divide by n. So this is very expensive. Yeah. This can take a lot of time to train. So there is another like formalization, which is the stochastic gradient descent, which doesn't do this. So it doesn't involve all the training set. So the previous one, this one is called batch gradient descent because it involves the whole batch, the whole training set. So the gradient descent minimizes the in-sample error, yeah, which is basically the average of the error over a single point xn, yeah. So E of the hypothesis, what is the hypothesis? Xn, and the label, yeah, that gives me an error. And I just average this over the n samples that I have. Gradient descent updates W by taking iterative steps along negative the gradient over the n sample error. Yeah, so W of t plus 1 is equal to W of t, the current W, minus eta, the gradient, okay, of the current weights. So it's based on all the examples, xn, yn, hence the name batch gradient descent. Now, the stochastic version works as follows. I pick one point xn, yn at a time. So randomly from my data set, I pick one point only. And then apply gradient descent to the error on this point alone. Yeah, so I compute error of the hypothesis of xn and yn. Okay, so 1 second. Why is it invalid? So I don't know how to deal with this as yet. Did he use the right link? Can you send him the link? Let me see if I can invite him. not sure how to invite him. I'm not really
Like boy.
What's that? Any thoughts on this? How do we invite? It worked. So Abbas is there?
Hello.
Yeah, I'm here.
Okay, good. So Abbas, we were talking about the following. We're saying, right, the last time we talked about gradient descent, which looks at the whole training set. So to update the weights, I compute the gradient over the whole training set. So I use the whole training set to compute the gradient. Okay. Now we're going to look at a different version that is called stochastic gradient descent that looks at a single training example. So I pick one example at a time and apply gradient descent to the error on this example. Okay. So what is the average direction? It's the expected, right, of the gradient on this example. Yeah, if I have infinite number of examples, then really the average direction is just the expected value over these examples of the gradient. Yeah, the direction is the gradient. The gradient decides the direction of the update. Okay, so what is it? How do I compute expected value when I have a finite number of samples? I just do average. So it's 1 over n, summation from n equal 1 to n, minus gradient of the error on the single example xn. What is this equal to? This is equal to the minus the gradient over the whole data set. So it's exactly the same. Overall, right, if I do on one example, so I update on just one example, I eventually get into the average direction that I get into is the same direction as if I've did the gradient on the whole data set. Yeah. So it's a randomized version of gradient descent. Called what? Called the stochastic gradient descent. So let's see the algorithm, yeah, in case you haven't followed all the details that I was talking about. So before we would have initialized the weights randomly, and then we would compute the gradient over the whole data set. So we had summation here, 1 over n, and summation from n equal 1 to n. So I'm looking at the whole training set, and I'm computing the gradient for it, right? Which is very expensive. If you have, hundreds of thousands of training examples, this becomes very expensive to compute. Now, instead, I'm looking at just one example at a time. So I shuffle the training set, so I, randomize the order of the training set, to add some randomization, and then I have two loops. One, right, just goes for a fixed number of iterations, and one that loops over the training examples. So for n equal 1, 2, 3 until n, I do compute the gradient over a single example. So what is the gradient of a single example? It's yn xn, 1 plus e yn w transpose xn. Why? Because I'm using the sigmoid function. Yeah, that's the gradient of the sigmoid function. So I'm just involving one example here. That gives me a direction, right, to get into, to update the weights for one example, to minimize the error on one example only, on the current example that I'm looking at. So update the weights w equal to w minus eta, the learning rate, times this gradient on one example alpha. Yeah, so I'm not looking at the global, right, error function. I'm looking at the error function with respect to one example alpha. Yeah, so I update the weight for this example, and then I move on to another example, update the weights based on this example, and so on. And eventually, right, after I go through one path through all the training set, so basically this is called an epoch. Going through all the training set means an epoch. So after I pass one epoch, I would update the weight multiple times, and I do few epochs. So I repeat, right, to pass over the training set, let's say 10 times or 20 times or 100 times, and that would be 100 epochs. And then return the final weights that you get. So the difference between stochastic gradient descent and batch gradient descent is that I'm in the stochastic gradient descent, I'm updating based on one example only, versus in the batch gradient descent when I'm updating based on the whole training set. Yeah, so I'm doing averaging here over the gradient. All right. Mhm. Can I show you what? Yeah. First gradient descent, right? The batch gradient descent, you have the average here. So you take the whole training set and you do averaging over, right, the gradients. So it's really expensive. Is it clear, Hamza? Okay. Here, you're doing it over a single example alone. And usually you need just few epochs and that's it to update the weight. Right? Okay, let's look at what's the difference between these two guys, the batch gradient descent and the stochastic gradient descent. The batch gradient descent is minimizing the error function, the real error function, yeah, the cross entropy error over the whole data set. So it's really taking steps right towards the minimum, right steps towards the minimum, very aggressive steps towards the minimum, yeah, because this is how gradient descent works. It tries to go, you know, a step further, right, update the weights so that I get into the minimum. Here's the minimum, yeah, these are the error contours. Stochastic gradient descent kind of like might diverge a little bit from the minimum. So because it doesn't see the minimum, it doesn't see the error function, the surface of the error function. So it could go right from one point to another, or from one update to another. It might increase the error a little bit rather than decrease. Yeah, so it doesn't go in this direction. It fluctuates a little bit, but on average, yeah, it goes into the minimum. It goes in the direction of the minimum. Why? Because we computed the expected of the average direction, and it was exactly as the gradient over the whole data set. So really, the stochastic gradient descent is, although it's a randomized version, it takes you on average in the right direction. It's the global minimum. This thing is the global minimum. Yeah, it's in logistic regression, there's one minimum only. Yeah, the function is convex. Okay? All right. So again, right, the batch gradient descent is faster to get you to the minimum. The stochastic gradient descent might fluctuate a little bit. Yeah, but let's see the advantages of the stochastic gradient descent. So batch gradient descent is very expensive. A single weight update involves the whole data set. So every time you update the weight, you have to compute, right, the gradient over the whole data set. On the other hand, the stochastic gradient descent is cheap. It's a single weight update, involves only one example. So I look at one example only, and based on it, I update the weights. So expensive versus cheap. Second thing, a whole pass on the data set results in a single weight update. So every pass on the whole data set, I look at the whole data set, that results in one single update in the case of batch gradient descent. In the case of stochastic gradient descent, a whole pass on the data set results in many weight updates. Yeah, because I update the weight every time I look at a point, update the weight. So by the time I pass over the whole data set, I update the weights n times. Versus here, right, a pass on the whole data set updates the weights only one time. All right. Now, batch gradient descent can be stuck in local minima or flat regions. In the case of logistic regression, as we said, there is no local minima. But when we look at neural networks, for instance, you can get local minima, yeah, or flat regions. So batch gradient descent can get stuck in them, whereas stochastic gradient descent would not, right? Because it adds randomization. So through randomization, it avoids optimization traps like local minima or flat regions. Let's see what this means. Let's assume this is the error function or the loss function. Okay, and I'm looking at stochastic gradient descent. So if I'm looking at batch gradient descent, then I might get stuck in this here based on where the weights started. So based on my, remember that the weights are initialized randomly. So I could have started here. So if I started here, it might tell me, right, go in this direction, that minimizes the error. And so I end up stuck here in this local minima. Yeah, because I update the weights based on the global error function. So I end up here. Yeah, but there is a better weights, right, that provide me a better error. I would not be able to see. Now with stochastic gradient descent, I'm not looking at the surface, I'm looking at every point individually. So I might start the weights here, go in this direction, yes, but then the next point makes me move in this direction. And so through randomization, I have a higher chance of ending up at the global minimum compared to the batch gradient descent. All right? Same thing happens with the flat region. So what is the flat region? So you assume the error function looks like this, but then it drops after a while. Yeah, so if I'm using batch gradient descent, I might look here and the error doesn't change. So I stop training and return these weights, assuming that these are the best weights that I have, the minimum. But then if I have trained for a few more epochs or tried, training for more time, I might get a better error. Yeah, so I might get weights with better error here that fall here. Yeah, this is what happens with batch gradient descent. With stochastic gradient descent, again, because I'm looking at at that single point, so I might get here, but then the next point might move me a very completely different space in the error function. Yes, I might have a better chance of getting out of the flat region. Right? So in general, it's preferable to use stochastic gradient descent than batch gradient descent for these various reasons. So most of the implementations you see of libraries, they use stochastic gradient descent. All right? Good. Now, stretch, we're going to talk about neural networks. Okay. So there is a lot of buzz around whether neural networks have been inspired by the brain or not, and here's my 2 cents on this. So the idea is we start from an objective biological function and imitate biological structure. Meaning what? Meaning that we know that in the brain there are neurons and they're connected to each other and there is activations and so on. And so we could, we were inspired by this when we created neural networks, right? We created neurons as well, and we have, they're connected to each other and there are activations, but that's pretty much it. Yeah, they don't work the same way. Yeah, the brain works in proteins and has biological functions, whereas neural networks work in a mathematical way. It's a purely mathematical model. Yeah, it has nothing to do with biology. Yeah, so it's just inspired by the brain, but has nothing to do with how the brain functions. This is similar to aeroplanes. So aeroplanes have been inspired by birds. They have wings, they have tail, yeah, but they don't function the same way as bird. A bird flies biologically. There is some biological method that makes a bird fly. Aeroplanes are purely mechanical. Yeah? So they're based on mechanics. All right? So the same thing here when it comes to neural networks. All right. So let's see the idea of neural networks. So we'll go back to perceptrons because neural networks are nothing but a series of perceptrons. So remember perceptron, it's a line or a hyperplane if you have the dimensions. And we have 2 dimensions. A perceptron breaking point is 4. Meaning what? Meaning that it cannot shatter 4 points. So let's see why. Let's see this figure, right? The first figure here. I have 2 positive here and 2 negative here. Can I realize this using a single line? Would I be able to, linearly separate these 4 points using a single line? Can I have a single line that separates these 4 points? No. The answer is no. Exactly. Yeah, we will not be able to do that, right? So if I have a line here, it will misclassify this point, right? If I have a line here, it will misclassify this point, and so on. So I really cannot separate these 4 points using a single line. But I can separate them perfectly using 2 perceptrons or 2 lines. Let's see how. So let's assume I have hypothesis 1 is this line. So everything that is on this side is positive, everything on this side is negative. And H2, everything on this side is positive, everything on this side is negative. Okay. Now, if I combine these two guys, I can say in this region, everything is positive, or in this region, everything is positive, and in this region, everything is negative, and in this region, everything is negative. So I can perfectly separate these 4 points using these two hypotheses, H1 and H2, or those two perceptrons, H1 and H2. Okay, so let's see what is the formula for this hypothesis that combines these two perceptrons. Any thoughts? So it's positive when H1 is positive and H2 is negative, right? So this is H2 is negative in this region, H2 is negative and H1 is positive. Or it's positive when H2 is positive and H2 is negative. Yeah, H2 is negative, H1 is negative here and H2 is positive here.
Sir, didn't you just say the solution?
What is the solution? Tell me.
No, it's positive when H1 is positive and H2 is not positive, so it's negative. And the second part.
Yeah. Or yes.
Isn't it?
Yeah, it's part of the solution. It's not the entire solution. When is it positive? It's positive when, right, H1 is positive or H2 is negative and H2 is negative, or when H1 is negative and H2 is positive. Yeah, so this is the whole solution. What is this called? Anybody know? So it's negative when both of them are positive or both of them are negative. So in this region, both of them happens to be positive, and in this region, X or exactly Z and Hamza. Yeah, so it's XOR between the two hypotheses. So H of X, the hypothesis that combines these two perceptrons, is the XOR of H1 and H. Excellent. Yeah, so basically now if I have, right, 4 points, I can realize them or shatter them using the XOR of two perceptrons. Yeah, one perceptron would not be possible, but two perceptrons would be possible. So it's a more powerful model. This powerful model is the XOR of two simple perceptrons. So let's see, how do I build logical functions using perceptrons? And then we'll see how do I build this XOR classifier, yeah, that combines two perceptrons. Okay. So let's see this figure here on the left. What is it? It's the OR. Again, so X1 and X2 is, again, we're assuming binary classification, right? So assume X1 and X2 are +1 or -1. Yeah. So assume that the input is +1 or -1. The feature values are +1 or -1. So this thing represents an OR. This is the sign. This is the hard threshold sign. So it gives me the sign of this signal. And the signal is what? Is the weight times the feature value. So I have here 1.5 times 1 plus 1 times x1 plus 1 times x2. That gives me the signal. And take its sign, and that should give me the ORing between x1 and x2. Okay, where ORing between x1 and x2 is the following. If both of them are positive, I get +1. If both of them are negative, I get -1. If one is positive and one is negative, I get +1. That's the definition of OR, the semantics of OR. Okay, right. So let's see if this is true. Why do we need bias here? So that I get to the OR. Yeah, the 1.5 will show. I'll show you why. Yeah, so basically, let's see what will happen if I just exclude this thing. Okay, so I have, let's assume that x1 was positive and x2 was positive. So +1 and +1. What is the signal here? It's
+1.
It's plus? The
Yes.
Plus what?
No, +1, right? It's plus.
plus 1 plus 1 plus 1.5. Correct? That's W0 times X0 plus W1 times X1 plus W2 times X2. That's 1.5 plus 1 times 1 plus 1 times 1. That's 2 plus 1.5, that's 3.5. What is the sign of 3.5? It's plus 1. So when both of them, X1 and X2, are positive, I get plus 1. Let's see the opposite. When both of them are negative, what do I get?
Minus 2 plus 1.5, which is negative.
Which is negative, so I get negative. So it's really realizing the OR. When one of them is positive and one of them is negative, they cancel each other, and I get sine of 1.5, that's plus 1. So really it is an OR, right? An OR is what? Is really positive when at least one of them is positive. Okay.
So shouldn't we use the features or just applying the weights?
So we're applying the weights, we're assuming the features are between positive 1 and plus positive 1 and minus 1. Yeah, just show that this is the OR function. Yeah, so it's a Boolean space. Okay.
Yes.
All right. Let's see if this is an AND. Can somebody try to tell me whether this is an AND or not? So anybody sees it? The only difference is that the bias is minus 1.5. Yes.
And we multiply them instead of adding them.
And what is logical AND? When is AND plus 1?
It's true when both of them are true.
Yes, it's true when both of them are true. So true here means plus 1, and false means minus 1. So this would be true if only both of them are true, or plus 1. So if this is the case, let's see. When this is plus 1 and this is plus 1, I get 2 minus 1.5, that's plus 0.5, so I get plus 1. When is it false?
When either of them is -1 or both of them are -1.
So let's try when one of them is -1. Let's say x1 is minus 1. So I get minus 1 plus 1, they cancel each other, and I get only minus 1.5. Sine of minus 1.5 is negative. So I get minus 1. And of course, if both of them are negative, I get minus 3.5. The sine of minus 3.5 is negative, and I get negative.
Okay. Why did we take the constant 1.5 mesh 1? Wouldn't 1 work just as well?
Try it out. If 1, would it work? If both of them are positive, I get, so minus 1, let's assume, minus 1. So
okay, plus 2 minus 1 is plus 1. As both of them are true, it's plus 2 minus 1, but see it plus 1. Okay, it's true.
Okay. And when it, 1 is plus and 1 is minus?
We get 0.
We get a 0, right? No, we get a 0 minus 1, so we get
0 minus 1, which is minus 1.
Yeah, yeah. And when both of them are negative, I get minus 1. So it's just it doesn't have to be minus 1.5. It could be minus 1 as well. You're right.
So this is why we need the bias, the 1.
Yeah, yeah. To get to the when both of them, because when one of them is positive and one of them is negative, it cancels, and you need the bias. Yeah.
Sorry, Atash, Wi-Fi, Andy, can you just repeat that last sentence?
So you could have basically minus 1 should work as well. And, it seems that minus 1 would work as well.
Okay, thank you.
You're welcome. Okay, so what are we doing? Yeah, we were here. We were saying, okay, it's powerful, right? If I combine perceptrons, I could, have a more powerful model. And then we went to logical functions. So what I'm trying to do is to say, how do I realize a perceptron like this? How do I build a hypothesis like this using perceptron? Something that is XOR, for instance. Okay, so let's see how it is. First of all, I'm gonna build it from end to the beginning. Yes, I had h of x was XOR of h1 of x and h2 of x, or h1 of x, h2 of x complement plus h1 of x complement h2 of x. So let's assume this is the input I was given was h1 h2 complement and h1 complement h2. Okay, this is the OR between them. We've just said this is the OR function. So I did the OR by setting the threshold to 1.5. That gives me the OR. Okay. And now I want to do H1, H2 complement. So what is H1, H2 complement? It's minus 1.5, H1, H2 times minus 1. That gives me the complement. Yeah. So it's the AND of H1, H2 complement. So that perceptron gives me the H1, H2 complement. Okay. Now let's see the other one. This one. Sorry, this one. It's again minus 1.5 because I want to do AND H1 complement H2. Yeah. So the red ones represent the H1 complement H2 case. Okay. I take the H1, H2 complement ORed with H1 complement H2. That gives me the final hypothesis that I predict. Finally, the inputs, right? I have input at the end. I have X1 and X2. These are inputs. Yeah, these are features. So I have a perceptron here, which has some weights, the blue weights. Yeah, these are learned using any learning algorithm. And this represents H1 of X. And this, the red, represents H2 of X. And then I add them, right, doing the complement. So I do XOR here. This is XOR. And then I get to the final hypothesis. So this is how I combine multiple perceptrons together. I stack them in layers. Yeah? So I create multiple, perceptrons, stack them in layers, called multi-layer perceptron. So this could be, yeah.
When do we output +1 and when do we output -1? يعني مثلا we can see مثلا 3 blue arrows coming from 1 and X1, X2, and then from this function we are outputting either 1 in blue or -1 in red. When
outputting 1 or -1, this is the weight of this edge. The 1 or the -1, this is the weight of the edge. So here I have a weight. Remember that the perceptron was what? Look at just one single guys of these. It's just a weight times feature values, correct? You sum, and that becomes the signal, and then you take the sign. That's the output. Now the output here, you take it and multiply it again by another weight. This happens to be 1 here, and -1 for this perceptron. Yeah, so the 1 and -1 are not the outputs, these are the weights.
Okay.
So you
sir, someone is telling the meeting will end in 2 minutes. The meeting will end in 2 minutes.
So what do we do? I'll start again and you guys go. Yeah?
Yes, make us all leave the meeting and then open it again.
Okay, okay. So I'll close, leave the meeting, and then we start again. End meeting, right?
Yes.
Did it end? No?
No.
No.
Okay, why is not working? Maybe I should stop share.